This is part 2 of a 2-video sequence on sampling distributions, the central limit theorem, and an introduction to inferential statistics. This video will introduce confidence intervals as a way to make inferences about a population that you otherwise know almost nothing about. Using the same setup that we did in the previous video, I've got some random values of x created here. These ones do not regenerate as I change things in the spreadsheet. And we no longer have a mean of 40 and a standard deviation of 10 as we did in the previous one. We're supposed to imagine this as 25 randomly selected values, and we don't know what the true population mean and the population standard deviation are. However, we can create estimates of those by doing some descriptive statistics. So over here, when we describe our sample, we've got 25 observations. That's our sample size, called n. I've calculated the sample mean x bar as 54.64. We might want to know the sample standard deviation. And there's a formula built into Excel called STDEV. So our sample standard deviation is 7.70. There we go. And we could also do things like create a histogram. We could identify whether or not the distribution of x appears to be skewed one way or the other. We might calculate the interquartile range. I might be a little bit curious about this value up here of 70. Then it might be an outlier. I see a couple values in the 40s, but nothing really stands out. There's a 44, there's a 45, 48, 47. Nothing really looks like an outlier on the lower end, but this value of 70 here might be interesting and worth talking about. Now, suppose we wanted to look at this sample of 25 observations of a variable that we'll just call x, and we want to know something about the population mean. We don't know what it is. If we had to pick a single number, you'd probably say, well, the mean of my 25 random values was 54.64, so my best guess is that the population mean of x is, give or take, probably about 54.64. However, I know that that guess, that 54.64, is probably wrong. It's also possible that the true mean is, say, 55. And just because of a little bit of random chance, we got some values that are a little bit lower than they were supposed to be, not enough values that were above the true mean of 55, and that's why we got a sample mean that was a little bit lower than expected. It's also possible that the true mean is 54, and we got a couple of values that were larger than we expected. It's also possible that the true mean is 60. Although looking up here, we've got only a couple of values that are above 60. I see 1, 2, 3, 4, 5, which means we have 20 values that are below 60, unless I miscounted. And it seems like a true mean of 60 is not real likely, although possible. Likewise, the true mean could be 50, and maybe just by random chance we got a lot of values that are above the true mean of 50 and relatively few values that are below it, although again that seems kind of unlikely. We could also say things like the true mean is 65 or 68, although based on our random sample here that seems extremely unlikely, and I would probably accuse that person of being a little crazy. Likewise, I could say that the true mean is 40 or 32. I could say that the true mean is 100. But based on the data that we've got, that claim probably isn't real likely. It would be extremely unusual if the true mean was 100 to get these 25 values as our random sample. Now we'd like to formalize that process a little bit and say, instead of just picking a single number for the mean of x and say, I think it's about 54.64, we should recognize that a single estimate is likely to be wrong, and we could instead use a range of estimates for values that are plausible. Now, from what we know from the central limit theorem, we know that whatever the true mean is, whether that be 55, 54, 58, 50, even 70, we know that values of x bar are likely to be within 2 standard deviations of x bar of whatever the actual population mean is. We would like to know something about the standard deviation of x bar, which we'll just call x bar because I can't draw a symbol in there. Well, from the central limit theorem, we know that the standard deviation of x bar, or of the sampling distribution, is the standard deviation of x divided by the square root of the sample size. We have the sample size right here. We have 25 data points. And while this is an estimate of the true standard deviation of x, it's likely to be fairly close. So this standard deviation here is going to be approximately 7.7036 divided by the square root of 25, which is 5. So the standard deviation of the sampling distribution is about 1.54. And if I double that, so I go 2 standard deviations, there's about a 95% chance that this value of x bar is within 2 standard deviations, or within 3 units, of the true value of the mean of x and the mean of x bar. That is, it's possible that the true mean is, say, 57, and this value of x bar would be about 2.5 units below that, which is within that 95% center range, within 2 standard deviations. It's also possible that the true mean is 55, and this would only be 0.4 units away. That's less than 1 standard deviation. It seems unlikely that the true mean would be, say, 60, because that means that this value of x bar, being 5.4 units away from the true value of 60, that's more than 3 standard deviations from the true mean of 60. Values like that shouldn't happen very often, and we would say it's probably pretty unlikely that 60 is correct. Now, since values that are relatively close to 54, say within 2 standard deviations below it or 2 standard deviations above it, would mean that values like 54 could happen within that 95% central range, we could also say that we're about 95% sure that the true mean of x, or the true mean of x bar, is probably within 2 of these standard deviations of x bar away from our best guess. That is, a plausible range of claims for the true mean would be our best guess of 54.64 minus 2 standard deviations, up to 54.64 plus 2 standard deviations. Now you could calculate those 2 values, and you'd have what's called a confidence interval. Notice how it was important that we use the central limit theorem here. We don't know anything about the distribution of x from which these 25 values came from, but we can guess that because the mean of those 25 values is 54.64, the true mean of x is probably somewhere fairly close to 54.64. Maybe a little bit above it, maybe a little bit below it. How far above and below? Well, the central limit theorem tells us that whatever the standard deviation of x is, we have an estimate of 7.7036. We know that the true standard deviation of x bar, of sample means, is that standard deviation divided by the square root of 25, the square root of the sample size. And we use that to say that this one value of x bar came from a distribution of all possible values of x bar with a mean that we don't know, but with a standard deviation that is probably about 1.54. That means that from our original guess of 54.64, if we go up and down 2 standard deviations, and we use 2 because that's the value associated with 95%, we can be 95% sure that the true value of the mean of x is probably somewhere within this interval, approximately 54.64 minus 3 and 54.64 plus 3. Now the other piece of the central limit theorem that we haven't mentioned yet concerns the shape of the distribution. We didn't say anything about whether or not the distribution of these 25 values, or the distribution of x, is normal. It could be a uniform distribution. It could be a binomial distribution from the discrete variables chapter, although this one doesn't appear to be discrete because there's decimals. There's all sorts of different distributions of x, or different shapes of distributions that these could have come from. Lucky for us, a third piece of the central limit theorem, the first two being that the mean of x bar is equal to the mean of x, the standard deviation of x bar is equal to the standard deviation of x divided by the square root of the sample size. The third piece is that regardless of the shape of the distribution of x, whether it's uniform, normal, bell curved, skewed, maybe it's bimodal and has 2 different peaks, the sampling distribution, that is the population of x bar, is always normal provided that your sample size is large enough. Large enough is just a rule of thumb. Typically textbooks say that large enough means bigger than 20, bigger than 25. Some textbooks will say bigger than 40. In today's world of big data, you'll see a lot of data sets that have 100 observations, maybe even 1,000 or 10,000, even 1,000,000. And the central limit theorem tells us that even if we know nothing about the shape of the distribution of x, we can always guarantee that the distribution of x bar is normal, and that allows us to, when we calculate these confidence intervals, use values of 2 to correspond to 95%, because those are the values that come from the normal distribution.